Hello and welcome. In this video, we're going to be talking about the derivative of natural log of x and the derivative of any function really that involves natural log. And we're going to start by reviewing some properties of logarithms, specifically natural log, and then we're going to jump into bringing the calculus in. So let's go ahead and get started. So in previous courses, you have worked with the common log, log, with different values, different bases, and you have worked with natural log, which is the inverse of the function e. In calculus, we really only see natural log show up in a way that makes any sense for us to be using in calculus, so we will eventually talk about how to convert between the common log, log, and natural log. But for purposes of what we're going to do in this first lesson, we are going to talk about the different properties of logarithms, how to expand, how to condense, what a logarithm is, and then we're just going to spend the first few minutes of this video reviewing those ideas before we start moving into how to do the calculus. It's really important that you understand how to manipulate things that have logarithms in them in order for you to be successful in this section. So if you need more than this video is giving you, please go check out a video that just talks about properties of logs. So some things to note. Right here we have y equals b to the x. That is an exponential function. Exponential function base b, notice it's not e here. An exponential function of this form has an asymptote at the line y equals 0. Also, the inverse of that would be y equals log base b of x, right? The base becomes your base of your logarithm. And this has an asymptote at x equals 0 because these two functions are inverses of each other. The next couple properties I want to make sure you take the time to look over are these two here, which are about expanding and condensing, and actually this one too that involves the exponent, the power. In order to expand or condense logarithms, which is probably the property that we're going to use the most in this section, you need to know that if we are adding two logarithms together and they have the same base, so in this case natural log, addition and multiplication go together. So if I had natural log of 2 plus natural log of 6, I could really say that that's natural log of 12. I could put them together and multiply. Or if I had natural log of 2 times x, I could split that to natural log of 2 plus natural log of x. So you can go back and forth in this way. Similarly, subtraction goes with division. So if I had natural log of 2 minus natural log of 5, that would become natural log of 2 over 5. Or the other way around. We can work backwards to expand. So when we go from multiple parts to one term, that would be condensing, making it smaller, versus if we start with something smaller and expand it out, that would be expanding. The last property of logs that we're going to use a lot in this section is that if you have the natural log of something to a power, that power can really drop in front. So we have that power times the natural log of that value of a. There's a couple other properties here that are helpful. We already talked about natural log and e being inverses of each other, which means natural log of e to what power is e? That would be 1. If we have log log, the common log, that is base 10 unless there's another number in that spot. So unless otherwise indicated. Natural log of 1 is 0 because e to what power is 1, e to the power of 0. And natural log of 0 is actually undefined. We can't ever have e to the power of something be 0. Again, that goes back to our asymptotes over here. A log is an exponent. So when you are evaluating a log, your answer is what exponent makes this true? Or the log is the power. What power makes this true? So when I'm looking at a here, I'm really asking myself 2 to what power is 8? 2 to what power is 8? And the answer there would be 3, 2 to the third power. So log base 2 of 8 is 3. Here, there's no subscript written there. That means that it's base 10. That's this property over here. So this is saying 10 to what power is 1? Well, anything to the power of 0 is 1, so this must be log base 10 of 1 is 0. Now for part C, this is really asking us e to what power is e squared? Well, that's going to be 2. On this last one, you could also rewrite this. This is the same thing, according to this property, as 2 times natural log of e, and we said that natural log of e is 1, so you can get 2 that way. So a log is an exponent. The question is saying what exponent gets you from the small number to the big number. Now let's focus on the skill that you really need for these lessons, and that is expanding and condensing. And actually, I would say expanding more so than condensing. So let's focus on expanding for these 3 examples, and then let's go ahead and jump into the calculus portion after we get there. So if I want to expand natural log of 5x squared, I'm going to use this property here. I am multiplying those things. That means I can split them apart with addition. But I could actually expand that further using this power property to say that this is natural log of 5 plus 2 natural log of x. These 2 expressions are equivalent, but one of them is expanded out. And again, you're going to see that expanding it out is going to make your life a lot easier in this class. I'm going to first rewrite this as natural log of 3x to the 5th times x plus 1 to the 1/2 power. And now I'm going to expand. This is the same thing, since these are all being multiplied, as natural log of 3 plus natural log of x to the 5th plus natural log of x plus 1 to the 1/2 power. And now I'm going to move the powers. This is natural log of 3 plus 5 natural log of x plus 1/2 natural log of x plus 1. So this is equivalent to this. And you might be thinking, I can't think of a reason why it's going to be more helpful for this to be expanded, but I promise you in just a few minutes you're going to see why it would help you to have these expanded. So for our last one, for C, this is the same thing as natural log of 2x minus natural log of that denominator. And then we could expand natural log of 2x to be natural log of 2 plus natural log of x minus natural log of x squared plus 5. So expanding means using those properties to stretch it out to make that almost longer, definitely more to write, but that's going to help us when we're working with derivatives. So let's go ahead and see what the derivative of natural log is. So we have been focusing a lot on integration. That's what all of chapter 4 was about. But what we didn't do is we never actually evaluated this integral here, which if you try and use what we did learn in chapter 4, you would think this shouldn't be too hard, right? I could rewrite this as x to the negative first power dx. If I tried to apply the power rule, I would add 0 to that exponent. Sorry, I wouldn't add 0. I would add 1 to that exponent, and then I would divide by my new exponent. But I'm hoping that right now you realize we have a problem here. This isn't going to work because I'm going to be dividing by 0, and I can't divide by 0. So the way that we have been evaluating integrals using the power rule, it works for every case except when that power is -1. So mathematicians really tried to look at what is this relationship, the area under the curve, because that's all this integral is, the area under the curve of 1 over x dx. They tried to look at what that area was representing. And they came up with a really interesting relationship that this area from 1 to some value, so 1 out to some value, is actually equal to the natural log of x. And if you're curious to the proof of this, you can check out my BC video that talks about this. It is also called the 5.1 video in the BC videos, and I will actually show the proof of the derivative of natural log. But what we're going to do right now is we're going to use the fact that if the integral of 1 over t dt is the same thing as natural log, then the derivative of the integral would be the same thing as the derivative of natural log. So again, if you want a more eloquent, detailed proof, it actually uses the limit definition of natural log, then you can go check that out. But what we're going to do is just use the fact that this relationship was discovered. So if I take the derivative, you could sort of think of taking the derivative of both sides, or taking the derivative using the second fundamental theorem of calculus on the right-hand side. The derivative of natural log of x is going to be 1 over x. And this is something really important that you need to know. And we'll focus on the integration aspect of it in the next video. But for right now, what you need to know is that the derivative of the function natural log of x is 1 over x. If there are more complicated things happening, if there's a chain rule situation, still what we're doing is taking the derivative of natural log, which is 1 over x. There may be other things going on, but that's the basic idea that we are going to do. So if I take the derivative of 2 times natural log of x, that's going to be 2 times the derivative of natural log, which is 1 over x, which this is just going to be 2 over x. Now, if you look at this next example, don't be fooled too much. You can use what we just reviewed about properties of logs to expand this out. So I'm not taking the derivative yet. I'm just going to rewrite this function. This is the same thing as natural log of 3 plus 2 times natural log of t minus 5t. So now if we take the derivative, f prime of t, this is a constant, so the derivative of that is just going to be 0. Natural log of 3 is just a number. The derivative of any constant is 0. Plus 2 times the derivative of natural log of t, which is 1 over t, minus the derivative of negative 5t, which is minus 5. So let's clean this up a little bit. This is going to be 2 over t minus 5 is our derivative. So expanding out your natural log values is going to make it easier for you to take the derivative. You could still take the derivative in the form that it's in here. So let's actually look at that same problem again, and let's not expand. If you didn't expand, this term here would have a chain rule situation that's happening. So this would be the derivative of the outside evaluated at the inside is 1 over 3t squared. And you would multiply that by the derivative of the inside. Well, the derivative of 3t squared is 6t, still minus 5. And then this would clean up to be 6t over 3t squared minus 5, which would simplify to be 2 over t minus 5. But if you just look at the amount of steps that I had to take here versus just expanding it out, I think you're going to see that expanding is going to make it easier, and you don't have to worry about the chain rule. Okay, let's work through some more examples. Okay, so here we go. On number 3, the very first thing I would like to do is rewrite this expanded. So I'm not taking the derivative yet. I'm just going to rewrite this as f of x equals natural log of 3 plus 2 natural log of x, because this exponent will come in front of only the term that has an x. Now if I take the derivative here, natural log of 3, the derivative of that constant is 0. The derivative of natural log of x is 1 over x, and that 2 is just going to go into the numerator because it's just a scalar being multiplied out. Here on number 4, if I expand this out first, I'm going to get y equals natural log of 4 plus 2 natural log of x minus natural log of x minus 1. So the numerator I'm expanding out using that product property and the power property, and the denominator using the fact that that division becomes subtraction. And now when I take the derivative, natural log of 4 goes to 0. 2 natural log of x becomes 2 over x minus 1 over x minus 1 times the derivative of that inside. So I have a chain rule situation happening here. The derivative of the outside evaluated at the inside is 1 over x minus 1. And then the derivative of the inside is just 1. So I actually kind of lucked out there. I'm going to leave this just like that. Now, I don't mind if you leave this in this form, not as one combined fraction. Some professors and some teachers might want you to combine them. You know, you can just find a common denominator to do that. Now, number 5 is a little bit different. Number 5 is going to involve using the product rule. So we have two functions. We have x and we have natural log of x. So if I take the derivative of, using the power rule, the derivative of the blue part, the derivative of x is 1 times natural log of x, keep the second function the same, plus keep the first function the same, and take the derivative of the second function. And then let's go ahead and clean this up. This is going to become y equals natural log of x plus 1, since this will become x over x, which just simplifies to be 1. Okay, let's look at a few more examples. I'm going to encourage you to try them on your own, but let me get them up on the screen first. Okay, I'm going to encourage you to pause the video and try and work through 6, 7, and 8 on your own, and then unpause the video and we will work through them together. Okay, hopefully you've had time to take a look at these. Number 6 is going to involve a chain rule because we have an inside function and an outside function. So I'm just going to make a little note here. Number 6 is going to involve a chain rule. So to take the derivative, we need to take the derivative of the outside. Well, the derivative of natural log is 1 over whatever I'm taking the natural log of, which in this case is sine of x. So the derivative of the outside is 1 over sine of x, times the derivative of the inside function, the derivative of sine of x is just cosine of x. So this is cosine of x over sine of x, which we know just simplifies to be, and actually you could leave it as cosine of x over sine of x, but it is good to remind ourselves that is the same thing as cotangent of x. Looking at number 7, I again have a chain rule situation, so 7 is also a chain rule. The derivative of the outside function, natural log, is going to go to 1 over 4x minus 1. The derivative of the outside, keeping the inside the same. Multiply that by the derivative of the inside. Well, the derivative of the inside is just 4, so I'm just going to leave that as 4 over 4x minus 1. Now for our last one here, number 8, this is going to involve using the quotient rule. So just like with the product rule, I'm going to treat natural log as my first function, I'm going to treat x squared as my second function, and I'm going to take the derivative using the quotient rule. So the derivative of natural log of x plus 1, that actually also is a chain rule situation. So the derivative of the outside, natural log, is 1 over x plus 1 times the derivative of the inside is just 1. So over here, we had to have a 4 in the numerator. Over here, we get to keep a 1 in the numerator because the derivative of the inside function is just 1. So there's, in red, is the whole derivative of our numerator. We're going to keep the denominator the same, so multiply that by x squared, minus, keep the numerator the same, natural log of x plus 1, multiply by the derivative of the denominator, which is 2x, and this whole thing is going to be over x squared, quantity squared. And I'm going to just rewrite this a little nicer. This is the same thing as x squared over x plus 1 minus 2x natural log of x plus 1. And this is all over x to the 4th. And I don't need you to simplify anything here. There's definitely a couple of pieces that could simplify. If I have x to the squared and x to the 4th, and I also have 2x and x to the 4th, I could split this into 2 fractions, and I could simplify it a little bit more, but that's not really the point of this video. The point of this video is making sure that you know how to work with and manipulate natural log when we're finding derivatives. So I'm going to just leave my answer just like that. Now, to recap what we covered in this video, we talked about what the derivative of natural log is and how that came from filling a gap that we didn't know how to integrate something to the power of -1. And that's going to lead us into our next video where we're actually going to talk about integrals that result in natural log. But for this video, we focused on how do you expand or condense using properties of logs so that you can take the derivative of a logarithm. So the most important thing from this video, what is the derivative of natural log of x? It is 1 over x. And if there are more things in play, then we apply the chain rule or the product rule or the quotient rule. But the most important thing here was the derivative of natural log of x is 1 over x. Again, if you're curious about the proof for that, check out my other video on 5.1 on the AP Calculus playlist, and you will see me walk through that proof. Go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.